everyone, and welcome to this video where I will try to go over a couple of problems and help you understand sections 7.4 through 7.6 a little better. Alright, so to start off, I'll just go over what sections 7.4 through 7.6 were on, just as context. To start, 7.4 was about increasing and decreasing functions. This means functions with positive and negative slopes. This first function is an increasing function. It's positive as it is pointing up. The second function is a decreasing function. It's negative as it is pointing down. And the third function is a constant, meaning it is neither positive or negative. It is either pointing up nor down. 7.5 was about stationary points, as well as the maxima and the minima. Stationary points in this graph are points A, B, and C. 7.6 was about optimization, meaning a mathematical technique for finding a maximum or minimum value of a function of several variables subject to a set of constraints, as linear programming or system analysis. Okay, so after those refreshers and that little context and background, we can begin exploring every section a little more in depth. Let's go! So as I mentioned before, 7.4 is about increasing and decreasing functions. Positive or increasing functions have a positive derivative, and negative or decreasing functions having a negative derivative. Remember that the derivative is related to the slope of a function, and this little diagram here is just to show you kind of like a visual of what I'm talking about. Decreasing meaning pointing down, and then at the bottom you can see f of x prime is less than 0, which means it's negative, and an increasing is pointing up, which means it's positive. As you can see, f of x prime is greater than 0, meaning that it is positive, a positive derivative. Another thing important for this section is a sign diagram. So sign diagrams tell you the stationary points in a graph and the way that it points in between, if it's positive or negative. The purpose is to visualize the derivatives and slopes of a function in relationship to their stationary points. It's helpful, especially if you're a visual learner, because it helps you literally see the graph and its directions, whether it's increasing or decreasing, and at what points it begins to increase or decrease, and at what points it is neither decreasing or increasing. Okay, so let's start with an example. This is example number 1. First, look at the function f of x. Here, we are trying to find the place in f of x where the values are not increasing or decreasing, and another point where the values are either decreasing or increasing, to construct what is a sign diagram, as I showed before. The first thing to do is find the derivative of f of x. So first, look at the function f of x, which says f of x equals 3x cubed minus 4x plus 23. We need to find the derivative of f of x because derivatives relate to the slope of the function. The derivative here is equal to 9x squared minus 4. If you use the power rule, you can find the derivative pretty easily. The next step is to find if the function is decreasing or increasing when x equals negative 5. To find the answer to this, it's very simple. All you have to do is plug in negative 5 as a value of x to 5x prime, which is the derivative of f of x, and solve. So the answer for here is positive 221. So we know that the function here is increasing because its derivative at this point is positive. Now we have to find a point in f of x where the function is neither increasing nor decreasing. This means that the derivative must not be positive or negative, and the only number that satisfies this is 0. So we must set the equation to 0. Setting the equation to 0 will help us find this value of x. So here we will use f of x prime, which is our derivative equation, and if you set 9x squared minus 4 to 0, and you do plus 4 on both sides, then you divide and do all of the things that you have to do, x equals 0.66. And with these, answers, we can make a sign diagram. Remember, the sign diagram is to help you visualize what we just found out in math terms. So this is what it should look like. 0 above 0.66, excuse me, because that's the place where it does not increase or decrease. That's the stationary point. Hint, hint. We know that at negative 0.5, the rest was positive, as we found that its derivative was positive 221. So we know that the way that the graph will look to the left of 0.66, which is the graph's 0, will be positive. And so that's why it is colored in blue, just to help you visualize that it has that plus sign above it to see that after this point, it's in a positive direction. So this is 7.4. It's not too difficult. You just have to know what you're looking at, and with these tools, it can be a pretty easy section. And the things that you learn here will be helpful for the following section, which is 7.5, which talks about stationary points as well as maxima and minima. So stationary points are points in the graph of a function whose derivative is equal to 0. The reason why their derivative equals 0 is because their slope is also 0. So the slope of the tangent, to the line of the function must equal 0. This means that they're not increasing or decreasing. They are constants, as I showed in the first section, 7.4, with the first graphs. These are graphs that don't increase or decrease. They aren't pointing down or up. They are a straight line, horizontal straight line. Like we found in the previous section, as I showed, they're not increasing or decreasing. Maxima and minima, as well as local maximum and local minimum, means the highest and the lowest value, local value on the graph. These points are stationary as well, because they are the highest. It can't keep going up or it can't go down if it's the lowest, so they have to be stationary, meaning that their derivative equals 0. So this is a diagram showing what I just talked about, local maximum and local minimum, and even a sign diagram at the bottom like before that is color-coded to show the changes in the graph. I suggest you copy it down if you're taking notes, by the way. You should be taking notes because then it's easier to remember and it's easier to study. Here we can see like the yellow part is positive because it's pointing up. It's a positive part of the graph. Then at negative 0.2, it's the local maximum because it's the highest stationary point in this part of the graph. And it's at negative 2, that's why there's a 0 on the sign diagram. Then it goes negative because the pink part is pointing down. And at 1, which is another stationary point, which is the local minimum, there's a 0. Then it goes up between 1 and 3. And then it keeps going up between 3 and the rest of the graph. That's why it's color-coded like that. The point of inflection is the point where it hits the x-axis. Yeah, and remember, something important to remember is that stationary points, the derivative equals 0 because the slope equals 0. So here's an example. First, you must take a look at the graph to the right and locate where points A and B are. If you see A is located at negative 4, 2, x equals negative 4 and y equals 2, and B is located at 3, negative 4, where x equals 3 and y equals negative 4. We also have another stationary point, negative 1, negative 1, and then we have 2 points where it meets the x-axis. So the first, number 1 says, what do the tangents to A and B look like? So this means if you were to draw a straight line that crossed A and it also crossed B, it was a tangent, so it only touches the graph at one point. Well, what they look like? Oh, I'm sorry. Well, what they look like. So for letter A, it would look like y equals negative 2 because it would be a straight horizontal line, and we know that A hits the y-axis at 2. And for B, it would equal y equals negative 4 because, again, it would be a horizontal line. And we know that B hits the y-axis at negative 4. So number 2 says, what are A and B? So since we've established that they are both stationary, since they are not increasing or decreasing at this point, and A is the highest point and B is the lowest, we can say that they are the local maximum and local minimum, respectively. From this alone, we can draw a sign diagram for f of x prime, which are the derivatives of f of x, kind of like what we did on the previous section. Only here we understand what is a local maximum and a local minimum. Your sign diagram should look a little bit like this, with the zeros atop every stationary point. This sign diagram demonstrates the values of the derivatives in f of x. It shows the local maximum and the local minimum of the graph and the way the graphs move, positive and negative, increasing and decreasing functions. So as we showed, there was a stationary point at -4, one at -1, and one at 3. And then in between, we can see the way that the graph moved. If you go back, you can see that between 4 and -1, it decreases, and between -1 and then 3, it also decreases. But apart from that, they are positive, so which means that the graph is increasing. Finally, we can move on to 7.6, which is optimization. The best way to solve for the optimum value in a math problem is to find two equations, one to maximize or optimize, and one that demonstrates the constraint. Then one of the equations must be solved so that there is only one variable to work with, and after that the derivative must be found. This is because the optimum or the maximum point, which is kind of like the local maximum, has a derivative that equals to 0 because its slope is 0, as we saw previously, because the maximum can't increase anymore and it can't also decrease. Then all you have to do is solve. For me, personally, optimization was one of the most tricky because you're dealing with two equations and various variables and things like that. You have to deal with those kinds of things when there are problems that include shapes, kind of like if you have a problem when a farmer is trying to build like a fence for his chickens or something like that. You need to like find area and perimeter, and you have to work with like what's the like best way, the maximum, the optimum kind of value in that kind of equation. But if they don't give you a kind of set equation or like a set kind of like rules, then you don't have to find that. For example, in example number 3, we have an equation v, right? We have an equation v, which is 3x squared minus 4x plus 77. So step number 1 would be to find the derivative of v. We need to find the derivative of v because, like I said before, the maximum value or like the optimum value would be the local maximum, which is a stationary point. So we need to find the point where the derivative would equal 0. So to find the derivative, use power rule. And here the answer would be v prime would be 6x minus 4. Then the next step would be to set v prime to 0 because the slope of a maximum point, like I said before, or the optimum would be 0. So if you set v prime to 0 and you solve for x, x would equal 4/6 or easier 0.66. Okay, now that I have done that, the final step would be to plug in this value into the original equation and find the optimal value of x. So once you plug 0.66 to the original equation, which would be what you're trying to find, this equation could be representing something like the total, like your total revenue if you're like have a business, or the total area you need for, like I said, if a farmer is building kind of like a house for its chickens or its, I don't know, pigs or something, then this would be a kind of helpful tool. For this particular problem, the answer would be 75.7, and that's how you would find an optimal value. Then we know that this point is a local maximum and its derivative is 0. Okay. Now that I've done my best to explain, it's time for you to do this on your own. You can go back in the video or check your notes if you've been taking notes like I advised, so that they can help you on your homework. These problems will be very similar to the ones that I have just discussed. Good luck! Okay, so here's the first problem. Now, you should pause the video now so you have enough time to solve it on your own, and then I will give you the answers. And here is the second problem. Pause once again so you can solve this on your own. It's important that you do it by yourself. You can use your notes, like I said. Pause the video. Okie dokie. So here are the answers for problem number 1. Did you get them right? I hope you did. If you didn't, try again. Look over your notes. Look over this video for the section where we talk about these kinds of things, and try it again. Keep trying. Here are the answers for problem number 2. How about it here? Were they right? Please say yes. If not, like I said, try it again. Look over what I talked about, look over your notes, and just try the problem again. There's nothing wrong with trying a problem multiple times. One of my math teachers used to say that practice makes better. So keep trying. Okie dokie, so that's all I have for you. I hope this video helped, even if it only helped a little bit. I tried my bestest. I'm not the brightest math student, but I tried. I tried to show you with the visuals and words and flowers. Keep practicing, keep asking questions, and keep trying. It's never a bad thing to keep trying. Retake that test, make those corrections, keep asking your teacher. Go, if they have study sessions, just go and ask questions, ask your classmates. Maybe somebody knows what you don't know, and maybe you know what they don't know. So help each other. Math is something that you'll always have to practice and become better with time, so I hope this helped. Ciao!